Hello everyone, welcome to Clarify X.
Have you ever stopped to think about how we can use the same set of rules to describe something as simple as a falling apple and as complex as a galaxy billions of light years away? Well, the secret, it's all in the universal language of physics, units, and measurements. Without them, physics is kind of just a bunch of ideas, but with them, it becomes the blueprint for engineering our entire world. So let's dive right in.
So just to show you how critical this is, let's start with a little thought experiment. What do you think happens when a team of absolutely brilliant engineers accidentally mixes up meters and feet? The answer isn't pretty. We're talking about a multi-million-dollar disaster. Yep, failed space missions, catastrophic failures, all from a simple mix-up in units. And that, right there, shows you why having a universal standard isn't just nice, it's absolutely essential. I mean, just imagine trying to build a skyscraper where every single engineer on the project uses their own unique ruler. It would be total chaos, right? Well, in science, that kind of chaos isn't just inconvenient, it's completely unacceptable. If we want to work together, check each other's results, and, build on discoveries, we all have to be speaking the same language of measurement. And that's where the idea of a unit saves the day. See, a unit isn't just a word like meter or second. It's more than that. It's an internationally agreed upon, totally standardized, and unchanging reference point. It's the simple, elegant solution to all that measurement chaos. Now things get interesting because not all units are created equal. We can pretty much split them into two main types. First up, you've got your fundamental units. You should think of these as the basic Lego bricks of measurement, things like length, mass, and time. Then you have derived units, which are what you build by combining those fundamental bricks. A perfect example is speed. What is speed? It's just length divided by time. See? Simple. So, to get everybody on the same page and bring some order to the world of science, pretty much everyone got together and agreed on one single system. It's called the SI, which is short for the French Système International d'Unité. It was officially established back in 1971, and it's the modern metric system that's become the universal language for all of science and trade. Okay, so if the SI system is our universal language, then what's its alphabet? Well, believe it or not, it all boils down to just 7. That's right, 7 fundamental or base units. And these 7 form the foundation for literally everything else. And here they are, the magnificent 7. You've got length measured in meters, mass in kilograms, time in seconds, and so on. Now here's the cool part. Every other unit in physics, I don't care how complicated it sounds, the watt, the Newton, the Tesla, every single one is just some combination of these 7 base units. If you can master this alphabet, you can read the language of the universe. So, we have our language, we have our alphabet, but how do we make sure our sentences, our equations actually make sense and aren't just gibberish? Well, physics has this incredibly cool built-in spell check for that very purpose. It's called dimensional analysis. At its heart, dimensional analysis is this amazing 2-for-1 tool. First, it's like a sanity check for our equations. Do the units on one side of the equal sign even match the units on the other? But second, and this is really cool, it can actually help us figure out the relationship between different physical things, sometimes before we even do a single experiment. And the process itself is beautifully simple, honestly. First, you just write down your equation. Then, you swap out every physical quantity with its fundamental dimensions, usually mass, which we call m, length L, and time t. After that, you just simplify it like you would in an algebra class. In the final step, you just check. Does the left side look the same as the right side? If it does, your equation is dimensionally correct. All right, theory is great, but let's get our hands dirty and put this to the test. We're going to use a classic equation for motion, displacement, S equals initial velocity, U, times time, T, plus 1/2 times acceleration, A, times time squared. Okay, let's break it down. On the left side, we have displacement, S. That's just a length, so its dimension is simply L. Easy enough. Now for the right side, Velocity u is length over time, so that's lt inverse 1, and we multiply that by time, t. The second term is acceleration, which is lt inverse 2 multiplied by time squared, t squared. Now look what happens. The t's cancel out in both terms, leaving us with L plus L. And since we can only add things that have the same dimension, this works. The equation is dimensionally correct. And just like that, you can see how powerful this is.
So, checking equations is one thing. That's super useful. But this is where it gets really cool. We can use dimensional analysis to actually solve problems. Let's grab a real-world example from a board exam and see how this works. All right, check this out. Here's a problem straight from the Tomonato board. We're given an equation for velocity, v equals a times t plus b times t squared. And the question is simple. What are the dimensions of that constant, b? Now, at first glance, that might look a little tricky, but don't worry, we have a secret weapon. And that secret weapon is called the principle of homogeneity. It sounds fancy, but the rule is incredibly simple. You can't add apples and oranges. That's it. In physics, it just means that every single term in a valid equation, anything separated by a plus, a minus, or an equal sign, has to have the exact same dimensions, period. So applying that principle here is actually really straightforward. If this equation is going to work, then the dimensions of v must be the same as the dimensions of the at term, and they have to be the same as the dimensions of the bt squared term. So to find the dimensions of b, all we have to do is set the dimensions of v equal to the dimensions of bt squared. Let's do the math real quick. We know the dimension for velocity, v, is length over time, or lt minus 1. Okay, so we set that equal to the dimension of b times the dimension for time squared, which is t squared. Now, just a little algebra, we divide both sides by t squared to get b by itself, and boom, there's our answer. The dimensions of b have to be lt minus 3. See? Simple as that. Feeling good about that? Let's do one more just to make sure this concept is locked in. This one's from an SCERT Tripura workbook. This time, the equation is for position, x, which is in meters, and t is time in seconds. We need to find the dimensions of c in this equation. X equals a plus bt plus ct squared. We're going to use the exact same logic. The principle of homogeneity tells us that the dimensions of x have to be the same as the dimensions of ct squared. Well, the dimension for x, a distance, is just length, L. So L equals the dimension of c times t squared. We just rearrange the equation to solve for c, and there we have it. The dimensions of c are lt negative 2, which, hey, if you're paying attention, you might recognize those as the dimensions for acceleration. So after that quick tour, let's just pause for a second and recap. What new tools have we actually added to our physics toolkit today? Okay, so your toolkit just got a major upgrade. You now have a universal language, the 7 base SI units. You get the difference between the fundamental building blocks and the things we build with them. You've got a built-in logic checker with the principle of homogeneity. And, of course, you have the ultimate spell check for any physics equation, dimensional analysis. You know, these aren't just some abstract rules from a textbook. They are the real, practical tools that every scientist and every engineer uses every single day to understand, to predict, and to literally build the world around us. So I guess the only question left is, now that you have the tools, what are you going to measure?